Hi, in this video, we're going to talk about how to implement removal in min heap. So what the min heap removal does is that it just takes the smallest element from the heap, returns it, and then delete it from the heap. So in a sense, it's a little different from removal in other data structure because usually what we do is, remove we specified which element to remove. But for min heap, we don't get to specify. We always remove and return the smallest one. So in other literatures, they're not necessarily called removal. Some of them refer to it as extract the minimum or something like that. But despite the terminology, the idea is the same. It's just remove the smallest element and returns it. So you can kind of imagine it's kind of similar to insertion, but slightly more complicated. And that's kind of a similar trend that we've seen with most other data structures that we study. The removal is slightly more complicated than insertion. So the algorithm to extract the minimum from a min heap is as follows. So first thing, we know exactly what a minimum is, right? It's always the first element of the heap or the root of the binary tree. So we remember that, and then because now we have to remove the root from the binary tree. So once we do that, then there's a hole um, to all the way to the left of the heap, and that would be it will no longer satisfy the shape property. Now to fix that, it's very easy. We just take the last element, the very last element from the heap, and just put it in the place of the first element. So that would bring us into compliance with the shape property. However, now most likely the heap property is not satisfied, right? Because that last element is mostly likely a pretty big element, and we put it at the very top of the binary tree, and the chance is it's bigger than many of its children or grandchildren, so on and so forth. So we'll employ the strategy of percolating, but instead of percolating up from the bottom of the tree like we do in insertion, we percolate it down until we find the right place for this element. And the complication comes from that when we're percolating down, um, there are two children, right? So which children do we percolate it down to, right? And when you think about it, it's pretty obvious that because the process of percolating down that element is kind of the same as pulling up one of the children, right? So we're doing a swapping. And so what we have to do is when we put up the child, we have to put up the smaller one so that it would maintain the heap property. If we put up the bigger one, then it will be bigger than the other children, the other child, and that's not good. So we just always pull up the smaller one. So to demonstrate how the algorithm works, we're going to use our favorite visualization tool. And the first thing I'm going to show is once we insert 5, 7, and 3, we'll do one removal. So we already have 5, 7, and 3 in the heap. So we will remove the smallest. So it takes away what's at the root of the binary tree, the smallest one, 3. And the next step is it's going to take the last element in the heap and place it in at the root position, right? So now it comes up to here. Uh, this should be deleted because it's no longer there, okay? And now we have this. The next thing we should do is, okay, now 5 is whatever is at the top. Let's see if we need to percolate it down. And in this case, it's very simple. It has one child. That one child is in fact bigger than the parent, and that's good. That's satisfied the heap property. So we are done. The next demonstration I'm going to do is a slightly bigger heap with two extra numbers. So this is what the heap looks like. everything is already inserted. So let's remove the smallest. Again, the smallest should be what's on the top. So that's 1, and that's the thing that we're going to return. Right? And the next step is we take the last element, which is 7. We're going to put it at the top. Okay, and since we already put it at the top, this last element can go away, so we can shrink the array, and it's already gone. Okay, so the next step is going to do is, okay, now that we're going to start percolating that from the root. So the first thing we have to do is to pick the smaller child of the two, and well, 3 is the smaller one, so we're going to pick that, and we're going to kind of pull 3 up and percolate 7 down to the position of 3. So that's what happens. And well, it decided it has to go this way, so swap the 2. And now once we're done with this step, you should recognize why we pick 3 out of the 2 children, right? Because 3 is smaller than 5. If we actually pick 5 and left 3 where it is, then we're going to put 5 at the top of 3, and that would violate the heap property. Okay, so now that we percolate 7 down one step, we're not necessarily done though. We still have to check, if we have to further percolate it down the heap. So we compare 7 to the child, the only child, 9, and in this case, well, it's already in the right order, so there's nothing to do, and we are done. So now that we've done a couple demonstrations, it's time that you try to do this thing on your own. So this is a slightly bigger data set. You should do this by hand first. I insert this into a min heap and then do a couple removals on paper, and then you can use the tool to kind of verify your results to make sure you get it, you understand it and get it right. Okay, now it's time to actually see how we write the code for removal. Well, I've already written the code out. It's slightly longer, but don't worry, I got lots of comments, and I'm going to explain it line by line. So the first thing we look at is how the removal, overall removal method works. So the first thing we want to do is, make sure it's not empty, right? If it's empty, we cannot return the smallest element. So in that case, we'll raise an index error rather than defining an empty heap error like we've done for binary search tree. And the reason for that is very simply, I don't necessarily like defining our own exceptions if we can use predefined exceptions. And index error is a good one, because if you actually say pop from an empty list, that's what Python would raise. So index error is a good exception to indicate that your heap is empty. All right, so the next step is that we know we're going to return the first element in the heap. That's the smallest one, right? So we remember that in the name, called return data, and that's what we'll eventually return. And then the next step is we want to get the last element from the heap, and we actually remove it and put it at the root, right? So very conveniently, Python lists allow you to just pop off the last element. So this just does that, and we'll remember it in the name of called last data. Now, one thing to be aware of is that it's possible the first element and the last element are the same element. That happens if the heap, when we start it, only has a single element in it. So if we do a removal on a heap that has a single element, then once we're done, the heap no longer has anything. So there's no percolation, anything that's necessary. So we'll only do percolation if there's something in the in the heap itself, and that's what this check is for. Okay, and so if there's still anything in the heap, then the first thing we'll do is that we remember we assign the last element to the first element, okay? And then we're going to do the process of percolating down, starting with the first element. So next we'll talk about how to do the percolating down. Now, one thing to know is percolating down actually takes a starting index that kind of tells us where to start the percolating process. This is not necessary for removal because we always start at the root, but in another method that we'll talk about later, we need that, and that's what the starting index is for. So the first thing we want to do is remember the data that we are going to percolating down. And then we do this as long as we are still within the bounds or the bounds of the heap itself, right? We don't want to go out of bounds of the heap. And so at each step, the first thing we do is, remember, we have choices of either left child or right child. We have to pick the one that is smaller. So we'll write another method called, get min child index, so that will return the index of the smaller child of the two. Now, it's possible that there's no child at all, right? And that's what this method will return if that, it returns none if there's no child at all. So in that case, well, we can't do percolating down anymore and we are done, right? And the element will be at the right place. So we break. The next thing then we do is, once we find the smaller child, we have to compare it with the data itself, right? So if the data, remember the data, is kind of at the parent place, right? So, and if the data is bigger than the smaller of the two children, then we have to pull the smaller child up, right? That's what this process does. And then we will move down to the place of the smaller child and continue the process of percolating down. Okay. Now, otherwise, if the data is already smaller than the smaller child, then it's in the right place. And in that case, we can just break out. And once we break out, we just assign the data, whatever the starting index at that point, it is the right place to put the data. So we just assign the data to that particular place. And then we are done. Finally, let me explain a little bit of what the get min child index does. So it takes a parameter that is the parent index, and it just check the left and the right child, right, and figure out which one is smaller. Now there's some boundary conditions we have to consider. So anyway, the first thing we want to do is we try to figure out what the left child is, and that's just the parent's index multiplied by 2. Now, if the index goes beyond the end of the heap, then there's no left child, right? And so we return none to indicate there's no child. Otherwise, we figure out, the right child index as well, which is just the left child plus 1. And then if now it's possible that the right child is beyond the end of the heap, which means there's no right child. And in that case, the left child is by default the smaller of the two, right? So the minimum min child index would be the left child in that case. Now, if the right child is within bounds, then we compare the left child to the right child. And if the left child is the smaller one, then the smaller child is the left child. Otherwise, the smaller child is the right child. And then finally, we simply just return the min child index, the index of the smaller child. Now that we've completed coding of the removal method, let's actually test it. So I want to explain how the testing is done. It's actually quite easy because we know exactly the order in which the data in the heap is removed, right? We always remove the smallest one, and once it's gone, the next one we remove is the second smallest one in the original heap, the current smallest one, right? And so on and so forth. So basically, the data, when they're removed, will be removed in the order from the smallest to the largest. So what we do here is, this is the set of data that we work in our demonstration earlier, and then we sort it, right? And for each single one of them, we'll just compare it to what we are removing from the min heap in the loop. So we should know, the first one we remove would be 1, and that's in the sorted list. And the second one remove would be 3 in the sorted list, and we continue to go. And here we keep a size. We also want to assert the size is correct as well. So we begin with the number of elements in the original data array, which it would be, I guess, 7. And every time we remove one, the size is decremented by 1, and we check the size against the length of the min heap and make sure it's okay. And then once we remove all the data from the min heap, if we do one more remove, we expect an index error, right? So I've already, as always, typed this out, and let's retro run this, and it works. Well, it took me a while to debug this, but now that it's totally debugged, the test works. So the last thing we want to talk about for removal is what's its performance. So pause the video for a bit, think about it. All right, assuming you thought through this, you should see this, that the most time-consuming process of removal, just like the insertion, is the percolating process, right? So in this case, it's for the element at the root of the binary tree to kind of traverse down the height of the tree, and potentially it might have to go all the way to the bottom. So again, it's proportional to the height of the tree, and again, because it's a complete and therefore balanced tree, the height of the tree is on the order of log of n. So the removal process is basically on the order of log of n.